Hello everyone, so let's look at what the effect of a common ion is on the pH of a solution. So in this example we're told to consider a scenario where a scientist determines the pH of a 0.15 molar hydrogen fluoride solution, which is 1.98. And then to that solution, so the solution of HF, we are told that they add enough Kf to ensure that the concentration of the Kf is 0.25 molar. We then ask, what is the pH of this buffered solution? We also need to compare the percentage ionization of the HF acid in both cases, in other words, before and after the addition of the Kf, and discuss reasons why behind what we observe in the calculations. Alright, so our first step is, what is the pH of the buffered solution? And because it's a buffer, your attention should immediately turn to the Henderson-Hasselbalch equation, right? Because the Henderson-Hasselbalch equation is the way that we calculate the pH of a buffer. So any solution that contains both the acid and the conjugate base, meaning anytime it contains the acid and the conjugate base, or the base and the conjugate acid, then you know you have a buffer solution. And then you can use the Henderson-Hasselbalch equation to calculate the pH of that solution, right? So what is the Henderson-Hasselbalch equation? It is pH is equal to pKa plus log concentration base divided by concentration acid. Alright, and specifically for this example, it is pKa plus log. So our base in this case is Kf, but of course it is the conjugate base of the acid, HF, so that means it's the F minus concentration, and the acid is HF, hydrofluoric acid. Alright, so some things that we need. So pKa, we can actually expand this a little bit, so let me do that. pKa, if we just quickly remind ourselves, pKa is negative the log of Ka, of the Ka, right? And this Ka is of the acid, right? So it's of the HF acid that you need to use. So you can look up the Ka of HF in a table, and you will see that it's 7.2 times 10 to the negative 4. All right. And what I then get is, so take negative log of 7.2 times 10 to the negative 4 plus log 0.25 divided by 0.15, right? Because the F minus concentration is comparable or is equal to the Kf concentration, and the acid concentration is of course equal to the acid concentration. All right. So, and we take it as the initial concentrations because we know the Kas is for weak acid, weak base, so the amount of ionization and dissociation is quite small. And that is what the Henderson-Hasselbalch equation is built on. It's built on the principle that the amount of ionization and dissociation is quite negligible, especially when these two species are mixed. And so you can take the initial concentrations to calculate the pH. Alright, so then I get a value here of 3.364, etc. So if we round that to two significant figures, so meaning two decimal places for the pH, I get 3.36. Alright, so that's the pH. Our next question is to calculate what is the percentage ionization in both cases. In other words, before the solution so just the HF on its own, and the buffered solution. So meaning when we have the mixture of the acid with its conjugate base. So let's first recall how do you calculate percentage ionization. So percentage ionization, so I'm first going to look at the buffer. Percentage ionization in general is equal to your hydronium ion concentration at equilibrium, right, divided by the initial concentration of whatever acid you are interested in, multiplied by 100%. All right, and the question here is, how do you get, so we know what the initial concentration of the acid is, or we know what the concentration of the acid is. It's given as 0.15 molar. And to get the hydronium ion concentration, always when we have the pH, we can calculate the hydronium ion concentration, right? So the hydronium ion concentration will be equal to 10 to the power negative pH, right? Because we just calculated the pH of this solution. It is 3.364, etc. So that means our percentage ionization here is equal to 10 to the power negative 3.364 divided by 0.15 multiplied by 100%. And if you round this, I got 0.288, etc. So that rounds to 0.29%. And yes, that is a low amount of ionization, because as you expect, the acid in presence of its conjugate base shouldn't ionize a lot, because there's already a lot of its conjugate base present, right? So it should remain mostly in its acid form. So makes a lot of sense. Let's look at the percentage ionization of the acid just purely placed in water. So in other words, that initial situation that the scientist looked at. So let's just call that the percentage ionization of just HF. And now with our knowledge that we are looking at, to calculate this, we're looking at 10 to the negative pH. The pH of a solution of just HF is equal to 1.10 to the power 189, and the concentration of HF is still 0.15. That's multiplied by 100%. I then get a rounded value here of 7%. So HF will ionize, 7% of the HF will ionize if it does not already have some of its conjugate base present in solution. And I mean, that makes a lot of sense. That is the effect of a common ion. A common ion will reduce the percentage of ionization of the acid, of course, and that is what we call a buffer solution, right? So a buffer solution will contains both the acid and its conjugate base already in significant quantities, and in essence it means that your acid is less ionized, your base will dissociate less, because those species are already present in solution. All right. Right, so just to end this example off, I want to show you an alternative method to the one that we did at the top here. So let's say, for example, you completely forgot what a buffer solution, how to determine the pH of a buffer solution, what buffers are, etc. Then you can use the ICE table method to calculate your hydronium ion concentration, right? Because what the buffer solution essentially is it's an equation where the HF is added to water, forms hydronium, and it forms its conjugate base. But what do you also have initially? You have your acid, but initially you also have some of your conjugate base present. Right? The only thing that isn't there initially is the hydronium ion. And then you set up your ice table as you normally would. So you need to figure out in what direction is the change going to occur towards equilibrium. Well, it makes sense that the reactants should decrease because one of the products aren't present, so that means the the reaction quotient is 0. So that means the forward reaction will be favored until equilibrium is reached. So that makes your change for your reactants negative and your product changes positive. And so at equilibrium, your reactants will have a concentration of their initial value minus X, hydronium will have a value of X, and your conjugate base will have a value of its initial concentration plus X, right? And you set up an equilibrium as such. The only thing is you have your conjugate acid with its initial concentration and your conjugate base with its initial concentration. All right. And then you use the Ka of your acid and you set up your Ka expression and you substitute in your equilibrium values as you normally would. And then you go about it and you solve for X. You can apply an approximation if the Ka value is small enough. In this case, I don't think it's small enough, so I just do a normal quadratic. And solve for X. Choose the appropriate value. I got 4.3 times 10 to the negative 4. And that's the hydronium ion concentration. And of course, the hydronium ion concentration then can give you the pH. And as you see, it's a very similar value. We get 3.37 compared to 3.36 from the Henderson-Hasselbalch equation. Right, and that's quite comparable. So you don't have to. So if, for example, you forgot completely how buffers work, you really can do it from the ICE table method. This is just a very long way. The Henderson-Hasselbalch equation, of course, is the approximation method. It's technically already the approximation included. So you technically already made an approximation using the Henderson-Hasselbalch, if you recall from the theory component that we covered. So, but should you forget about that, then you can treat this, the ICE table method, and you can treat it as an equilibrium where you have a common ion, both of them, and use the hydronium ion concentration to calculate the pH. It's also perfectly reasonable, and even though you might say, oh, 3.6 and 3.7, that's not significant, that's basically the same pH. So, yeah, that's just for interest mainly. Remember, buffered solutions, you use the Henderson-Hasselbalch equation. Makes the most sense. But should you feel the need to use an ICE table, if you're more comfortable with that, that's also perfectly fine. It's just a bit more work. Alright, thank you for watching, and I'll see you in the next video.